All right, everybody, welcome back. In about a minute or so, we're going to welcome, actually, I'm going to start right now. Great. So our first speaker for today is Dr. Ralph Mcnutt. He is the principal investigator for this study, and he has been the driving force behind this last 4 years of work that many dozens of people have taken part in. And I have enjoyed this ride quite a bit. He has been fun to work with. And challenged all of us to keep coming back to two basic things. One, what is it that we can do with the tools that are available now to enable this very exciting idea about space exploration? And two, make sure that what we have can be shared with everybody as rapidly as possible so that people can reach in to this work and see what's going on. His vision behind this has driven all of it, and I hope you enjoy his talk. Ralph, the floor is yours. I'm going to mute myself, and I will drive the slides for you.
Okay, thanks, Michael. So with an intro like that, I've got a lot. Hopefully I will measure up to it. Michael, you're quite kind. Well, anyway, good morning, everybody, and thanks for joining. It looks like we're up to about 82 participants, so that's good for the day. So what I thought I would do is to go back and provide a summary of summaries. I mean, as Michael was saying earlier, you're going to be hearing a lot of detail about where we are with the study over the course of the next several days. So this is really sort of a précis of where we're going. Some of this will be duplicating things from where we started. Some of it will be new. And what I wanted to be able to do is to show you how things have evolved over the last 4 years. So Michael, if you could go to the next slide, please. So let me just remind everybody that from the very beginning, we've been talking about this as a pragmatic interstellar probe with the emphasis on pragmatic. It's through the outer heliosphere and into the nearby very local interstellar medium. And the idea is to use today's technology to really take the first explicit step past the Voyagers, actually designing a mission. The Voyagers, thankfully, are still operating. They're going to be operating for a while longer, but they are running out of power. And basically, again, to remind everybody that hopefully this will not be the end. This will be the beginning, perhaps, of a new era of exploration. Remind everyone that really trying to get out into the far reaches of the heliosphere began with Pioneer 10 back in March of 1972, and with Pioneer 11 following it, Voyager 1 and 2, and now New Horizons, and perhaps Interstellar Probe as well in the near future. We've really made inroads into looking at what the area around us looks like in the galaxy. Next, please. So again, Michael had mentioned that we were basically tasked by the NASA Heliophysics Division to study this mission again, and this started back in June of 2018. So we've been at it for a while. Right now we're finishing up on the sort of the next phase, what we call the next phase, which is really the engineering background. And the plan is to actually have a report, as Michael mentioned, that we're working on now, out on the street and available to the public before the AGU meeting this fall. We're on schedule for that. And this would be available for not just for NASA headquarters, but for everyone around the world as input to the next Solar and Space Physics Decadal Survey. Trying to really sum up where we are right now with looking at this mission concept. Next, please, Michael. So let me just remind everybody that the modern era of astronautics really started out with the novelist, with Jules Verne and with H.G. Wells back at the end of the 19th century. And it's ideas and it's people that start these things off. Next, please. And then we get the engineers and the other thinkers and the scientists to come in as well. And sort of the people that were inspired by Verne and by Wells included Tsiolkovsky in Russia and Goddard in the United States. And both of these people were actually thinking about how to get out of the solar system and explore the space between the stars, already thinking in the early part of the 20th century. So this is not a new idea. But again, we're re-looking at a very old idea. Next, please. So officially, with respect to the beginning of the space age, even still, this has been a long time in the making. The National Academy of Sciences and the Space Science Board, what as it was called at the time, was looking at what one could do with space in the early days of the space age. From March of 1960, one of the things that was flagged then was an outer solar system probe, which they simply said something to be aimed from the sun in the plane of the ecliptic, with the parenthetical note that it is hoped that motion away from the sun to the extent of 5 or 6 astronomical units per year could be accomplished by 1965. That was a bit optimistic. Remind you that Voyager 1 is now the fastest thing that humanity has ever built leaving the solar system, and it is traveling at about it's on the order of about 3.6 AU per year, and that's hard to do. So we're going to talk a little bit more about how to get the speed up and get back to where people were thinking we could be, perhaps as early as 1965. Next, please. So again, it's been a long, strange trip through a lot of different concepts, starting with that report. Gene Parker, of course, everyone knows, I think that's certainly in the science community, who pioneered the theoretical work in understanding the solar wind. Parker's solar probe is named for him. And Gene was actually thinking about this mission as well as early as 1965. The Voyagers, of course, launched in 1977. There were a variety of studies looking at an interstellar probe mission along the way then, starting in 1990 and throughout the early 2000s, and coming up to 2015. And if you go to the next slide, please, Michael. So sort of a reboot in all of this was a couple of workshops that were run by the Keck Institute for Space Studies out at Caltech. This was in 2014 and 2015. Once again, looking at what one might be able to do with an interstellar probe mission, and again, looking back at these previous studies, and then looking forward to what it might take to really finally get a mission selected to go forward. Next, please. So the scientific questions really are not new, and that's going to be one of the themes that you're going to hear more about today. Panos Brandt is going to be talking a lot about that, as well as some of the more detailed discussions in the following days. There was a large JPL study that was done in 1976, 1977, and it was on the eve of the Voyager launch, if you think about it. And the primary objectives and the secondary objectives that were outlined then, you're going to find, are very similar to a lot of what we're going to be discussing this week, and indeed have been discussing over the last several years with this study. At the time, they were talking about dropping off a Pluto orbiter on the way out of the solar system and using a very large nuclear electric propulsion system in order to do the mission. Again, things that did not exist at the time, and one of the reasons for thinking about the pragmatic approach is to try to actually have something that we have technology that we can use to accomplish this mission in the near term. Next, please. So Interstellar Probe Science Goal and Opportunities, you're going to be hearing a lot about this, again, from Panos and others. That really the primary goal is the way that has been framed in the course of this study is our habitable astrosphere and the unexplored interstellar medium. Of course, we're learning things with the Voyagers all the time, which are out there, and we're learning that, as not surprising, that there's a lot that we do not know, and there are a lot of unexpected things that we're still learning. We of course know that our atmosphere, our astrosphere is habitable because we are here. But the question is, well, what else is out there? What do some of these other systems look like? And what are the consequences there? And again, something that's been a great deal of study that's been going on recently. There's also astrophysics opportunities and planetary science opportunities. We've learned from New Horizons, for example, about with respect to the Kuiper Belt, that there's a lot still to learn there, but you have to get out there to go by to see them. So one of the things that we were asked to do by NASA headquarters is to take a look at what other things that could be done besides heliophysics. And this has formed what we call the augmented mission, and you'll be hearing some more detail about that as well. Next, please, Michael. And again, astrosphere habitable. So we've got that. So the purpose of the study, here we go. Thank you. So the purpose of the study is we've got a box that is shown here in the lower left-hand side of the figure that shows 3 different characteristics: downlink, communication, power, how much power I've got on board of a spacecraft, and the longevity, which is reads out as 50 years. And so the idea is to be able to, what we took a look at was, suppose that I've got 300 watts left at the time of the end of a mission, and suppose I can make the mission last for as long as 50 years, and suppose I might be able to get out as far as 1,000 AU. How well could I actually use current technology to be able to match something to that box? And then, oh, by the way, I have to have compelling science. Otherwise, there's no reason to do this. And so then the question is, if I take that box, what kind of compelling science can I put inside of the box? And so that's really been the scope of the study as we've gone forward. Next, please. So again, the central question really has always been propulsion. I've already alluded to that. The issue has always been in these past studies that the near future capabilities have been the backdrop for defining the requirements. But the real issue that we face, and we face in all sorts of space robotic missions that we've contemplated and that we've flown and that we'd like to do in the future, is to unite the compelling science and engineering with technical reality, something that I can actually pull off. Next, please, Michael. So when we set all this up, we had a variety of tasks and an overall approach. This goes back to 2019, and then was projected forward to December of 2021. And let me just step through this. So Michael, if you could just step with me, and we've of course looked at the science again. We've looked at the concept of operations in order to be able to do that science as I step my way through our own heliosphere and out into the helios sheath and then into the near interstellar medium. We've looked at longevity, again, targeting 50 years as a lifetime. The Voyagers were designed to last for 4.5 years. To do this mission, we really need to be able to have something that will last. Instruments, we've taken a look again at instruments. We've taken a look at defining a baseline payload. You'll hear more about that. Next, please. Trajectory and launch vehicle. Michael's already alluded to the fact that we're looking at the SLS as a baseline launch vehicle, one of the classes of the super heavy lift launch vehicles that people have been talking about. Next, please. We've looked through communications and guidance and control trades. Next, please. We've looked at the so-called O-berth maneuver in quite a bit of detail, going close to the sun and seeing if one could actually get a lot of more speed out of the system by a close solar flyby. Finally, we've taken a look at a mechanical design that will actually close for the mission. And then finally, next please, Michael. We've been looking, of course, at power, and again, June Zakrajik is going to be speaking later in the week, talking about where that NASA is with respect to radioisotope thermoelectric generators. All those come together. Next step into concurrent engineering. You've got to have a solution that closes. Next, by 2020, we had an interim report. Next, we had workshop input in the virtual workshop last year. Next. And we had a report out of that, and we're going through that as well. And next, please. That's about where we are there. And again, coming up to the final report. Go to the next, the next slide. So we started out with a notional science traceability matrix several years ago, and basically a baseline as well as an augmented part. I'm not going to belabor this because I just wanted to remind everybody where we started all of this. And if I could go to the next one, please. We've gotten a little more sophisticated. So there's been a team of about 80 people, both within APL and from around the world, volunteers, working very, very hard over the last one or two years on trying to see what would make sense for a science traceability matrix to really look at the compelling science case. again, updating us from where the previous studies have been on this. Of course, it's always the idea of starting with the goals, mapping that through all the way through the mission requirements, mission phases, and then finally getting it down to closure. In other words, have you been able to answer the science? And Panas, again, is going to be doing a more detailed job of that in his talk coming up. Next, please. So readiness, near-term implementation. We've said that we want to be able to launch by the year 2030. That doesn't mean that that's the best thing that makes sense in terms of policy or in terms of targets, but it sets a line in the sand for when that you have to have technology ready for, so that you can't just simply kick the can down the road. And again, the use of a super heavy launch vehicle to implement this, we've baselined the Space Launch System. We've looked at available upper stages, because if you need to develop a new stage, you have a rocket program, you do not have a research program, because developing new stages is something that is very complicated, time consuming, and expensive. And then finally, we've identified existing instrumentation that could address the science, so that we could have something that we could actually look at in terms of cost and in terms, again, of closure on the system. And Michael, if you could go to the next step on this. So I just wanted to illustrate this. The SLS is coming along. This is from the RS-25 engines, main engines on the main part of the booster. This is from the Green Run hot fire test number 2. This took 8 minutes of firing, all quite successful. This is run at Stennis Space Center in March of 2021. And again, the SLS is a reality. The hardware is out there. This is being built. It is going to fly. There have been some delays in the program, but we're moving forward, and Rob Stoke, again from NASA Marshall, is going to be talking about this in more detail later in the week. Next, please, Michael. So payload examples, I've mentioned about this as being a community effort. Again, Panas and Alice Kokoris are going to be talking about this. We've put together a baseline payload and an augmented payload. Again, examples, and this has been really much been a community effort, pulling things together to take a look at what the mass and power resources might be, and what might be the sort of costs that would be involved with something like this. Next, please. So the mission concepts are all ballistic. We've not looked at low thrust in space concepts, because everything that's out there is really limited by their mass to power ratios. And I'm including everything from solar sails to nuclear electric propulsion. That's a different discussion, but again, with keeping with the pragmatic theme and with something that we would be ready to launch in the 2030s, we have looked at simply at ballistic ideas. There's 3 options we've looked at. One is an unpowered Jupiter gravity assist, which of course has been used by the Pioneers and the Voyagers and New Horizons to get up some extra speed from using Jupiter's orbital energy in the outer solar system. We're also looking at the idea of an active Jupiter gravity assist. One of the ideas that has floated around for a long time is actually doing a burn at Jupiter by carrying a stage with you out to the outer part of the solar system. But there's been no real solid engineering set of design traits, and so we've undertaken that. And then finally, I mentioned about doing a burn very close to the sun. Again, something that's been talked a lot about, but we've actually put a lot of meat on the bones in terms, so to speak, in terms of looking at details of what some of the engineering issues would be in doing that. We've had, looking at various stages that we put together, there were 181 cases we have gone through, and 130. One of those provided potential solutions, and then we have been able to pick the best solution out of all of that. Next, please. Mechanical layout for options 1 and 2. Basically, it's something that looks like Voyager on steroids. Shouldn't be a surprise to anyone. The main thing that you're looking at is the communications high gain antenna, 5 meters in diameter. If I'm going to try to be able to communicate with a decent data rate from these far reaches of space, hundreds of AU out, I just simply need to have an antenna that can help to handle that. I also need to have 2 radioisotope thermoelectric generators. We've baselined something. We'd start the mission out with about 600 watts of electricity, and then be down to something on the order of about 300 once that we get out to the 50-year mark. Next, please. So in terms of trying to look at what we could do in terms of going close to the sun, we've actually contracted as part of the study with a company in Idaho Falls, Advanced Ceramic Fibers, looking at some new unique ultra high temperature materials that also have low weight. And we've actually used those to come up with some conceptual designs for thermal shields to see how close we could really get to the sun with a spacecraft, and use that as a baseline for actually doing some real engineering trades using some of the experience that we learned about in designing the thermal shield on Parker Solar Probe, but kicking that up a notch and looking at what it would take to get within, say, 2 solar radii of the center of the sun, a lot closer than Parker is going to be going. Next, please. This is a mechanical layout for something like that. You can see that the thermal shield really would dominate the spacecraft, about 1,600 kilograms. This is the lightweight version. This is with the spacecraft and attached to a Orion 50 XL kick stage. It's something that would burn near the sun. So this is probably the highest potential performer that we've been able to come up with in the course of the investigation. And this will be highlighted in some of the other talks. Next, please. So I mentioned that we had quite a few different concepts. This gives you an idea of what we looked at. The plot is showing the time to the given distance in years, and across the bottom is the distance traveled. This is from 0 out to 30 years. You can see that there are 2 distinct branches. The lower branch all starts out at 5 AU from the last Jupiter encounter. And then the ones at the top actually start out near the sun. These are for option 3. And if you could go to the next time step, Michael. This maps us all the way out to several hundred AU and out to 50 years. The red arrow points out that for the cases that we have looked at, this is for an 860 kilogram spacecraft, about the same size as Voyager, to be able to accommodate the kind of science payload that the community has identified for this particular example. We could get out to about 375 astronomical units away from the sun in a flight time of about 50 years, well into the nearby interstellar medium. Next step, please. The baseline heliophysics option, this is going to be talked about in more detail later. Basically, I have a launch opportunity to get out to Jupiter once every 13 months or so. These are these red zones. Depending upon when I fly by Jupiter, that determines where that I will actually be flying out into the outer part of the solar system. And so the launch year basically tells me where that I can access the various parts of the heliosphere. And there are several options we've laid out. Again, there'll be more discussion about this, but probably something in the launching in the 2036 to 2040 time frame would be where that one would probably want to target for the science. Again, with the idea that I've got something that I could certainly build as early as 2030 without any sort of critical technologies that would have to be developed. Next, please. Power, close to historical and planned. The numbers that I gave you are very close to what we've got on both on the Voyagers with the MHW RTGs, as well as on New Horizons, and flew on Cassini with the GPHS RTGs. Right now, NASA is working on coming up with what are called the next gen RTGs mods. These should be ready for flight with characteristics such as one would need for interstellar probe, with the first units being available for flight in the late 2020s. I think the aim point's around 2027 at this time. And again, June Zakrajik will be talking more detail about those. If I go to the next time step, Michael, this graph just shows you what the decay of power looks like. And with a half power point, and after about 50 years is about where we've been able to get with the silicon germanium converters. And again, much less than the half-life of plutonium-238 itself, but nonetheless, there is aging of those converters, and that really sets the lifetime of these power supplies. It's something that people that are involved with Voyager and New Horizons are very well aware of. Next, please. Spacecraft reliability and longevity, you'll be hearing more about this. We've had a big part of the study has been looking at, can I build a spacecraft with a design criterion of lasting for 50 years? And the answer is yes. You have to pay a lot of attention to engineering, to parts, to testing, to physics of failure, methodology, but it is a doable thing. Next, please. Telecommunications, we've been looking very seriously at that. Currently, of course, we've got the Deep Space Network. If we were really to be able to get out to as far as 1,000 AU, which is a bit of an overstretch from given the rest of the analysis that we've done, but nonetheless out to several hundreds of AU with a high data rate, we're going to need something like the capability of the next gen VLA to be able to do the communications. So this is something that one would have to be thinking about developing in terms of ground station capability in the future. It actually turns out that it's something that is actually opens the gateway for international collaboration, because with a little bit of appropriate knowledge, anybody on the ground with ground stations can contribute to getting the data back from Interstellar Probe from the nearby Interstellar Medium. Next, please. So Michael alluded to this earlier, that we're also in the process of doing some cost estimation. That's underway, and this is going to be a large strategic mission, but we think that this is something within the scope of what was done for Parker Solar Probe. Of course, the SLS is another issue that one has to worry about, and nonetheless, it is true that while the SLS is being developed for the Artemis program to get humans to the moon, there are significant advances in science that could be accomplished that the SLS would be enabling for, or another vehicle that has those sorts of characteristics. Next, please, Michael. So for any mission, there are 4 key elements. There's a case for going, the science, we've been looking at that. There's the means to go, that's the technology, we've been looking at that. One has to have the agreement to go, that's the strategy, and that's going to be the place of the upcoming decadal survey to take a look at this and to take a look at the other things that one would like to do in science and in heliophysics coming up for the next decade, and then come up with a strategy of what it would take to go forward. And then, of course, you've got to have some policy, because you've got to be able to fund these things. Next, please. So this is one of many possible scenarios. This would be for a launch in August of 2036. It's a short video here. Let me just talk you through this. So the SLS will be launching out of the Cape. This is the Block 2 cargo version that will be coming up and be ready in the late 2020s, early 2030s. It's currently on schedule for development to help to take cargo up to the moon. Launch, of course, is largely being driven by the large solid boosters that are developed from the solids that were used on the space shuttle. The core is a liquid oxygen, liquid hydrogen stage. That takes us on up to heading up toward orbit. That uses the RS-25 engines that were just tested at at Stennis Space Center. We get staging to the exploration upper stage. This is the next stage up. It uses RL-10 cryogenic LOX liquid hydrogen engines. Again, the vehicle meant to go to the moon, but in this case, we would go up to a parking orbit around the Earth, line up for trans-Jupiter injection, fire up the EUS again. After that burns out, we would fire up a Centaur upper stage. And after that burns out, we would fire up a Star 48 BV stage to inject us into orbit to Jupiter. The heliphysics baseline would be a spinner. We would spin that up, get rid of the solid rocket booster, turn ourselves around, link up with the high gain antenna back with the ground stations on the Earth. Basically, after the launch, we would cross the lunar orbit in about 6 hours. This has got twice the energy of the New Horizons launch. Somewhere out near the moon, go ahead and deploy the magnetometer, deploy also 50-meter long electric plasma wave sensors, about a 7-month flyout time to Jupiter, and rapidly crossing the orbits of Saturn and Uranus and Neptune, and finally Pluto, getting out, crossing the termination shock into the heliosheath, and then past the heliopause into the nearby interstellar medium. So basically, as soon as checkout was finished near the Earth, this is an all-science mission. We'll be looking through several different solar cycles, all the way across the solar system and out. And with that, I believe I am done. And thank you for your attention. Michael, back to you.
Thanks, Ralph. So we have until 11:20 on the schedule for questions for Ralph. If you go to the Q&A session tab on the Zoom, you can ask questions of Ralph, and he and some of our other panelists may be able to join in and answer them. If Ralph's covered a lot of ground here, we've got 20 minutes ahead of us here, and you'll note that I believe Andrea, help me out here. Do we still have the vote up function on the question and answers, or is that an older version of Zoom?
I think we might need to see if that can be enabled. So hang on one second while I work on that.
Shall I go ahead and address the question that's there? We've got one question in the Q&A
yes, please.
section. So the question says, can be deferred if it will be covered elsewhere. Why is there no mention of optical communications? Was this considered? And it will be considered. It will be talked about elsewhere, and it was considered. The issue with optical communications, and even with Ka band, is pointing accuracy. One of the difficulties that one runs into is that I have to be able to point things very accurately in order to be able to use those higher frequencies, especially optical comm. And the issue that one runs into is that the best way of doing the pointing is with reaction wheels. And reaction wheels have finite lifetimes. They tend to run out, and nobody knows how to build reaction wheels that will last for 50 years. So we took a very conservative approach here and said, well, okay, so if we're really serious about lasting for 50 years, we're probably going to have to use X-band, and we'll have to design the comm system around that. And I believe Jim Kennison will be speaking more to that later. And Michael, we're getting more questions, so I'll let you officiate for what you'd like me to talk about next.
For now, we can take them as they come in. Tony Freeman asks, how long is the Jupiter encounter, meaning the period during which useful science measurements could be made at Jupiter, I presume?
It's going to be very short. And one of the questions actually is going to be to what extent that we will actually have instruments on as we come by Jupiter, because we will actually be coming down to right over the cloud tops at about 1.05 Jovian radii in Jupiter's equatorial plane or near that. So we will be coming right through the worst part of the radiation belt. We've taken a close look at that, and it turns out that the integrated fluence of radiation is not that bad because we are moving so fast. So we're talking about order of hours or days at the very, very, very most. And again, whether we'll actually have instruments on or not during that time period is something that needs to be studied some more. But the opportunity is potentially there, and there will be probably things to do. And let's see, I've got an estimate. Is there an estimate of the total cost of the mission? Yes, actually, we're working on that now. I can tell you that if I look at Parker Solar Probe, it ended up coming in, if you don't include the launch vehicle, and there's a reason for that. Parker Solar Probe came in a little. I think the number is about $1.3 billion, something like that. And if I take those dollars and inflate that forward to the early 2030s, I'm going to be getting up to close to about $2 billion before I have the launch vehicle. So again, this is going to be a large strategic mission. I'm not going to be able to do this on the cheap. It's going to take significant resources, but not so significant that they're resources that NASA has not historically had. there's been a lot of discussion about, well, what does an SLS cost? And there's also the question of, well, what's the price of an SLS going to be if it's being used by the Science Mission Directorate for enabling science missions? And this one's a complicated policy issue that goes to the heart of some of the things that NASA is thinking about right now. And Rob Stokes going to be talking a little bit about this, I think. One of the issues with the SLS is that one has to keep the supply chain up and running. And so there's sort of it doesn't work if you build one and then you go back and 4 years later you say, well, I'd like to build another one. And so one of the things that actually could happen is that with looking at some of these science missions that could be enabled with the SLS, it may be a very good partnership across all of NASA to be able to have a need for these large vehicles, in which case that will help to bring the unit cost down somewhat, and will also help to keep the supply chain running. So a lot of complicated policy issues there, but that's sort of where we are looking in terms of what we think that the costs might look like. Let's see here. Thrusters, plasma dynamic thrusters.
So Ralph, I'm going to read the question so that everybody can. So
Right.
This is from Nibin Sabari Anand. Forgive my pronunciation if it's off. It says, "Hi Ralph, how important is thrusters to the spacecraft, and insights on utilization of plasmodynamic thrusters, and how does the GCR, the galactic cosmic rays, and SEP determine the spacecraft's longevity and radiation protection techniques?"
Right. So I would say we haven't gotten down to the nitty-gritty of deciding exactly which thrusters that one would actually end up buying for attitude control. Again, what's going to be the guiding principle is going to be that we have to have something that's got demonstrated long lifetimes. Not quite sure what the state of the art is in terms of lifetime on plasma dynamic thrusters. That's something that perhaps Jim Kennison can discuss in his talk coming up. We have indeed looked at galactic cosmic rays and solar energetic particles in terms of exposure to the spacecraft. Basically, most of the exposure that we tend to get is during that Jupiter encounter, but it's so fast that it's not that big of an issue. Even with being out there for 50 years and being out for a substantial section of that time out beyond the heliopause, where we're seeing down to the lower energy galactic cosmic rays. I don't have the numbers off the top of my head, but we have looked at that. And again, standard engineering practice with what I do with spacecraft in the outer part of the solar system will work. And we don't have any issues there that other than just being careful again with the parts that are going to give us any problems. We're not going to have to worry about, for example, a radiation vault such as one has on Europa Clipper, for example, because the radiation levels won't be nearly that high.
And we have a question from Bill McKinnon. I presume Juno data tells us how dangerous ring dust impacts will or not be at 1.05 Jupiter radii given interstellar probe flyby speeds. And Ralph, this actually stems from a question that I answered by typing an answer as well. That Marshall Eubanks asked: is it within the ring zone? Is 1.05 is our Jupiter flyby distance in the rings of Jupiter?
And we've taken a quick look at that, and so we're not exactly in Jupiter's equatorial plane, thankfully, and so we're in order to be able to do some of these to maximize our speed out of the solar system. And again, there'll be some other details of exactly what the aim point looks like. We can actually miss the bulk of where that the ring material is. Again, it's one of these things that we've taken a quick look at. As long as we're a couple of degrees off the equatorial plane, shouldn't be a problem. And Bill McKinnon's right. We've certainly got data about what the Jovian ring dust system looks like. And again, one has to be careful and one has to be aware of it. And we did take a look at it, and looks like we're okay.
So we had a question that Pontus provided some typed answer to already. The question from Nicholas Donders was, what is the time frame to cross the TS compared to the Voyagers? Thank you. And Pontus says that with the current speed, it will take only about 12 years to reach the TS, the termination shock of the heliosphere, and about 16 years to get to the heliopause. Exact times depend on the final direction of the launch itself. Compared to the Voyagers, Ralph, how long did it take Voyager to get to the termination shock compared to how fast we'll be going?
Well, let's see. I've got to remember all the numbers, Michael. It was this. So this is going back into the 2000s. We were out there for some 30-ish going on 40 years to be able to do that. So yeah, this is basically what we're looking at here is a speed that's about twice as fast as Voyager 1 in terms of the asymptotic speed outside of the solar system. It's sort of the best way of looking at it. So right now Voyager 1 is traveling about 17 kilometers a second. That's about 3.6 AU per year. We'll on this again with a Voyager size payload and a Voyager size spacecraft, we would be up at about 7.2 AU per year. That's about 35 kilometers a second. Again, by using an optimized Jupiter flyby.
You know, Ralph, could you also say a little bit about how this speed, not a lot faster than these speeds, but how this speed sets the mission up for a nice set of reasonable long but reasonable chunks of time where one phase of the mission occurs and then another occurs and another occurs?
Yeah, that's a good point. I'm sure Pontus is going to, and some of the others are going to go into this in more detail. One of the things that we had a lot of discussion about was, well, okay, so suppose you could go really, 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 really fast, and a lot faster than we're talking about here. And we had a lot of the people in the science community said, well, wait a minute. Well, there's a lot that we don't know about the heliosheath. We certainly know it's there. We know that it's an intriguing plasma regime that we really don't understand. And you don't want to be going so fast that you simply go right through it and aren't able to actually look at the plasma sheath as this interesting plasma regime on the way out. And so there's been a lot of back and forth about that, a lot of discussion over the last several years. But it's sort of the 7.2 AU per year has sort of ended up being kind of what people have perceived as the Goldilocks solution. It's not too slow and it's not too fast. It's sort of just right for being able to really make advances in our understanding of this critical part of the heliosphere system that's helping to protect our planet from galactic cosmic rays out there as well. And it also means that I've got as I would be voyaging out from the Earth out to the 50-year mark. Of course, this means that I'll have the chance of actually being able to see the heliosphere through several solar cycles, which, of course, is a driver of a lot of the dynamics. And we've got, of course, cuts with the Voyagers and with the Pioneers for some of the solar cycles before, but it's a limited amount of data, and having more of those kind of scans with those 11-year periodicities from solar activity in sort of in the back of one's mind means that we'll have a better chance for really understanding the time variation of the system.
And actually, Matt Hill provided a very specific answer for us, Ralph. With the 1977 launch, Voyager 1's access to the termination shock looked like it was 2004, so 27 years.
Yeah, okay.
Whereas in our case, it'll be about 12.
Yeah.
So thank you, Matt. John Cooper asked, radiation noise may be, or states that radiation noise may be an issue for some instruments since Interstellar Probe goes into the very local interstellar medium unshielded by the heliosphere.
Right, and John's absolutely right. I mean, again, there's going to be more of a radiation background than we're used to having if you're inside of the heliosphere. We know from the Voyager measurements how much that the low energy GCR flux has come up. And so this feeds directly back into the kind of parts program that you're going to have. It's going to feed back into exactly what kind of shielding that you are going to need on the instruments. But again, we've taken an initial look at that, and it's not anything that really is that extreme. I mean, the parts program on the electronic parts on a mission like this to carry out for 50 years, one's going to have to be careful about that anyway. But again, nothing has really been identified as being outside of current engineering practice, and again, certainly nothing so complicated as needing to have some sort of a radiation vault for the mission.
Thanks, Ralph. I think we have time for one last question here. Nibbin asks again, what destination is targeted for this particular mission? The interstellar medium in between the heliopause and the Oort cloud, or the interstellar medium that is beyond the Oort cloud and all the way near to Alpha Centauri? And will solar sail really be the most lucrative approach to AU distances? Okay,
we're not going to the Oort cloud.
Well, his question is, are we targeting the interstellar medium between the heliopause and the Oort cloud? And the answer is yes. The
answer to that is yes. So the Oort cloud, if you think about it, the Oort cloud is, extends out to sort of the balance point and gravity between the sun and other nearby stars. Current thinking is we're talking about something about a light year out, so that's about 64,000 AU. We're not going to be going that far. So again, it's getting it. If the Voyager's got our feet wet, well, then this is going to get us out into the waist deep water, but we're not going to be out in the deep ocean with this mission. Again, it's a next step. If you'd asked the Wright brothers back in 1903 in Kitty Hawk, what would be their plan for flying an aircraft with 300 passengers on board to London from New York? Well, maybe they'd have gone back to working on bicycles instead of trying to get the first airplane off. So one has to do this again in a reasoned way, step by step. But this would be the next step, and that's part of the pragmatism in looking at this mission. It's again, it doesn't mean it'll be the last step, but it's the next step to take, and we're ready to do it now.
This idea of solar sails. It's important to remember the premise on which this all got kicked off, which is what can we do with the technologies that are available now? And if we want to use instruments that we know can achieve the science that we want, a solar sail really isn't going to be able to carry a payload heavy enough to do the science that we believe the community would like to carry out there. And maybe we could send a really tiny chip out to some speed, probably not, given the current sail technology capabilities, as fast as the solutions we already have with conventional propulsion. And that's been a big part of the work we've done, is to make sure that the speeds are achievable, and that the technology, the instruments themselves, and the spacecraft, that it all closes, that it all comes together, as Ralph talked about, and is a mission that we could put forward to say, hey, this can be done in this time frame.
Well, and that's an important part about the closure, because again, you have to have the science, you have to have the closure there. What we've come up with is, again, a spacecraft that's on the order of the mass of the Voyagers with a payload that's on the order of the Voyager payload mass. We're talking about around 80 kilograms to 90 kilograms of instruments in order to do the science and in order to really make the compelling science case. And so this is way past where the current state of the art is with what people are looking at for solar sails. Again, there's Solar Cruiser that's going to be coming up here in a few years. It's going to give us sort of a next step on where we are with solar sail technology. But in order to try to fly the kinds of payloads we're talking about in the 2030s with solar sails, that I think is a real stretch. So again, we sort of are where we are, and another subject for debate at another venue, perhaps.
All right. Well, Tony Freeman provides a comment that we've taken the Portuguese approach to exploration as opposed to the Spanish, who sailed off the edge of the world. I don't know enough about the difference between the two exploration approaches to appreciate the joke, but yes, we're definitely not trying to sail off the edge of the world.
This is not being envisioned as Magellan's voyage, and there is which I think is being alluded to here. And there was one other quick question about why are you baselining one spacecraft, not two?
Yeah.
Upwind and downwind. Well, as a matter of fact, the Chinese Space Agency is looking at exactly that for a type of an interstellar mission that they would be launching that would perhaps about the same time frame as we're talking about, but certainly not nearly as fast. And basically, the question always ends up with cost. If we'd be more than happy of launching 2 or 3 spacecraft as long as somebody could come up with 2 or 3 times the money that's already for a large strategic mission. So you have to worry about the money at some level.
And I can't think of a better way to wrap up your presentation than Bill McKinnon's comment, Prince Ralph the Navigator. All right,
I don't know about that one. We'll see. The ship's not paid for and built yet.
All right, and there are other comments rolling in about Portuguese exploration and so forth. So we are up at 11:20 Eastern time. Forgive me. We're going to take a 10-minute break. We'll be back at 11:30 with Pontus Brandt, talking about the science for the baseline mission. Thank you very much, Ralph. If we were in a big room, I'm sure people will be clapping. So all right, I'm going to mute myself. Ralph, you can go ahead and do the same, and we'll be back in 10 minutes, everybody.
Sounds good. Thank you, everyone.